We've been talking about the effects of natural selection on allele and genotype frequencies. There's a couple other points about natural selection I want to make today. We're going to look at frequency-dependent sexual selection, two other types of natural selection, or special cases, if you like. Then we'll do some more practical problems. And then we'll move on to talk about the other causes of evolution. There are 5 things. Besides natural selection, they include genetic drift, gene flow, recombinant mating, and mutation. Those things will be covered on test 2. We're not going to cover them on test 1, but we'll start talking about them today. Also, when we get to it, we'll start on chapter 5, which is on the subject of speciation, essentially the type of macroevolution that creates new species, as opposed to just changing the frequency of alleles and genotypes. First of all, before we can understand how these species are created, we need to first of all figure out how to define species. And there's several different ways of doing that. One way is through the biological species concept, which relies on reproductive isolation. But there's also other ideas about how species are defined, and we'll look at those as well. So that speciation is in chapter 5. Everything else here is in chapter 4. Okay, so just to remind you, once again, we redefined evolution as a change in the genetic makeup of a population or the genetic structure. That simply means a change in the allele and or the genotype frequencies in that population. And as we discussed before, there are 5 things that can cause that change to occur. And so far, we've only talked about natural selection, and we're going to continue to talk about that for a little while for the first half of our class today as well. We saw some examples of different kinds of selection in action. So we looked at an example of natural selection against the recessive allele. We saw that kind of selection tends not to completely eliminate the allele that's being selected against, because natural selection can only act on phenotypes. You have to not homozygous for that to work. On the other hand, dominant alleles are expressed whether they're homozygous or heterozygous. The selection against the dominant allele could potentially be 100% effective in eliminating that allele. We also looked at how natural selection works on quantitative characters, where you don't have distinct or discrete phenotypes. Instead, you have a continuum of variation. An individual will show a trait that falls along a gradient from very, very low to very high. So you can have this kind of variation in height, for example, size, skin color, and so on. You don't have discrete categories that rather are. We saw that in this situation, you can have directional selection, where natural selection eliminates one tail, that normal distribution, or you can have stabilizing selection, when it eliminates both tails, or you can have disruptive selection, when it eliminates the ones in the middle, and creates a bimodal. So different kinds of selection operating on different traits. Okay, a new type of selection that I want to start off with today is frequency-dependent selection. This kind of selection occurs when the effect of the trait on fitness depends on the frequency of that trait. In other words, it depends on how common the trait is in the population. Now this is a cichlid fish. Its scientific name is Parasotus microlepis. And I don't even think it has a common name. It's a fairly obscure fish. It's an endemic fish in the Great Lakes of Africa. So that's the only place in the world where it's found. Now, the fish is a predator, but it has a kind of an unusual way of feeding. It feeds by picking scales off the bodies of other fish. And sometimes that can include fish that are much bigger than itself. Now, within this species, there are 2 different morphs, or 2 different varieties that coexist with each other. We have, on the one hand, the right mouth morph, which has a mouth that's kind of curved over towards the right side of its body. And then there's the left morph, hard to say 10 times fast, that curves over in the opposite direction, towards the left side of the body. Now, this is a target fish here that's being stalked by a Parasotus. The right mouth morph, because the mouth is curved towards the right side of the body, it has an easier time attacking the target from the left side. So it will tend to sneak up on the target from the left, pick off the scale, and then zoom away again before the target can react. On the other hand, the left mouth morph, that mouth twisted the other way, it'll tend to approach from the right side, pick off the scale, and zoom off. Okay, so the right mouth morph attacks from the left side, whereas the left mouth morph attacks from the right side. Give me one second. Let me see if I can do this. Now this chart here shows the frequency of left mouth individuals in the population, showing the frequency of the left mouth traits, left mouth morph. The data started being taken here in 1981. You can see that in that year, the frequency of the left mouth morph was about 60%. So about 60% of the fish in the population had the mouth that twists over towards the left side. Now this chart doesn't show the frequency of right mouth morphs, but we don't need to see that. If we know the frequency of the left mouth, we automatically know the right mouth morph. What's the right mouth frequency in 1981? It was 60% of the left mouth. Starting point. Frequency right up to 1. So if the population is 60% left mouth, then it's also 40% right mouth. So that was the ratio in 1981. The left mouth was the dominant morph. Now fast forward 2 years, and we see that, in fact, the situation is now reversed. In 1983, we see that the left mouth morph has decreased in frequency. Now it's down to about 40%, which means that the right mouth morph has increased to about 60%. Now it's the left mouth morph which is more rare, and the right mouth morph which is more common. Fast forward another 2 years, the situation is back the way it was in 1981. The left mouth morph is up to 60% again. Fast forward 3 years, and we see that now the left mouth morph is down to about 45%, but the right mouth morph is more common. So it appears that these morphs oscillate in frequency over time. We see a gradual oscillation in terms of which morph is the more common morph in the population. So why does this oscillation occur? Well, according to one hypothesis, it's because of frequency-dependent selection. When the left mouth morph is most common, the mouth this side is more common, the prey tend to become vigilant on the right side of their body. They learn to expect an attack to come from this direction. So they're kind of looking over their right shoulder, waiting to see if the fish is going to sweep out the route towards them. And that gives them the ability to react and avoid the attack. So basically, the left mouth morph is at a disadvantage because the prey is willing to expect an attack from the right side. On the other hand, the right mouth morph now has a big advantage because the prey are looking the other way. It can easily zoom in from the left side, grab a scale, and fly off again. So it has very good feeding success. So as a result of that decrease in feeding success, the left mouth morph has more trouble getting enough food to reproduce. Its fitness drops, and its frequency begins to decline in the population. But the right mouth morph starts to increase in frequency, and it's getting lots of food success. So you see this drop in frequency from 60% to 40% for the left mouth, and increase for the right mouth. Now eventually, at this point here, the right mouth morph becomes the most common morph. And prey now switch their attention to their left side. They now expect the attack to come from the left. So they're looking over their left shoulder now, and they see a right mouth morph coming away. But at the same time, they're now getting attacked more frequently by the left mouth morph. So the frequency of the right morph drops, the left morph goes up, and we see that switch back to the usual situation where now the left mouth morph is more common. Now this is an example of what we call negative frequency-dependent selection. When fitness decreases as a trait increases in frequency. In other words, the fitness of individuals that have that trait goes down as the trait becomes more and more common in the population. So having a right mouth phenotype is advantageous when that's a rare phenotype. But when it's a common phenotype, then it becomes disadvantageous. And that's when you're going to get negative frequency-dependent selection. I'm just going to draw what that looks like on the drawing. we make a graph that shows on the y-axis fitness, the fitness specifically of individuals with a trait, we graph that against the frequency of that trait in the population, from low to high. We're going to get a line with a negative slope. So when the frequency of the trait is low, individuals that have that trait have high fitness. On the other hand, when the frequency becomes high, then the fitness drops in frequency. In fitness. This kind of selection puts a brake on the increase in frequency of any particular morph. When morph stresses become too common, it becomes less fit, and that stops it from becoming more common. And that allows multiple morphs to coexist together over a long period of time in the population. Rather, a long-term coexistence of morphs that have this kind of so the cichlid fishes are a good example of this kind of frequency dependence. You can also have positive frequency dependence. When fitness increases, the frequency of a trait increases. Now, this is also known as when fitness increases and the trait increases in frequency, you're going to get positive frequency dependence. This is also called purified selection because it will tend to eliminate all but one morph in the population. An example of this kind of selection you often see in plants that have different colored flowers in the same species. We have different colored morphs. For example, these are morning glories here. You can see that the flower color varies. Different color varieties of morning glories. Now, many pollinators will tend to develop a preference for the morph which is most common in the population of flowers. They tend to look for a certain flower pattern. And when they see that, they home in on it. And they become accustomed to searching for the most common type of flower available. So they may tend to overlook the less common flower varieties over the one which is most common. So those common flowers get more pollinator visits. They have more success in getting pollinated and diseases, and therefore their fitness increases. They become even more common, while the less common morphs get few pollinator visits. Poor reproductive success, and they become even more rare than they were to begin with. So that's positive frequency dependence. And the graph for that looks a little bit different. Okay, that's our negative. This is negative frequency dependence here. Positive frequency dependence. The graph looks like this. And when a trait is infrequent, rare, it's also relatively fitness associated with that trait is also relatively low. When a trait is very common, the fitness is high. So what tends to happen is morphs that are already common become even more common over time. Morphs that start off rare become more and more rare over time until eventually one morph, those rare morphs are eliminated and just one morph survives. The one that is most common to begin with. So that's positive frequency, and it's also known as purifying selection. It will tend to eliminate morphs rather than promote coexistence of rare morphs. Another case of frequency-dependent selection occurs when it's a predator which is searching for prey rather than a pollinator. That's referred to as predator-mediated frequency dependence. Predators are often similar to pollinators in that they tend to focus their attention on the most common type of prey that's available to them. They tend to develop a searching image for that most common morph, and that's what they preferentially attack. Now these are typical water babies here. Aquatic insect that is fed on by other kinds of aquatic insects as well as fish and other predators. And these water boatmen come in 3 different color modes. They vary from very light brown to very dark brown. And it appears that frequency-dependent selection occurs in water boatmen. In this case, because of predators that are feeding on them rather than because of mutuals. Now, this was an experiment to show this frequency dependence in operation. So, in this experiment, they offered a mixture of water boatmen of 3 different colors, pale brown, medium brown, and dark brown, to predators to see which morph would be eaten preferentially by the predator. And they did several different trials in which they altered the frequency of the 3 color morphs of the prey. So on this graph here, we see the percentage available to the predator, the percentage in the mixture that's offered to the predator, versus the percentage the predator actually eats. You can see that if we look at the pale brown morph, when the pale brown morph was offered at a frequency of about 25%, so it made up only a quarter of all the water boatmen that were offered, the predator attacked it at a frequency of only around 10% or so. Even though they made up 1/4 of all the water boatmen that were offered to them, predators only fed on them about 1 time out of every 10. So they were disproportionately avoiding that rare morph. It's like they developed a preference for the other morphs and they were ignoring the light brown one. On the other hand, here we see another trial where the frequency of the light brown morph was increased to 50%, so they got it was the most common morph out of the 3. And now you can see that the rate of attack is about 60%. Even though 5 out of 10 boatmen were light brown, they were being attacked 6 out of 10 times. So now, the predator developed a preference for them when they became more common. This green line here shows the series of points on which the percentage available is equal to the percentage eaten. So in other words, where there's basically no preference or no choice shown by the predator. The predator is just attacking the predator. If the points fall below the line, that means the predator is avoiding that mark. And if they fall above the line, then the predator is preferentially selecting that mark. So you can see that a particular morph may be avoided or preferred, depending on how common it is relative to other morphs. So this is a question we can try with your clickers. Does coloration in the water boatmen undergo positive or negative frequency-dependent selection? Feel free to discuss it before we do. You think that water boatmen will go positive or negative frequency-dependent selection? Okay, I'll close that in 10 more seconds. It's exactly a 50-50 split. Half of is positive, half of is negative. Well, unlike a pollinator, it's a good thing to attract the attention of a pollinator, but it's not a good thing to attract the attention of a predator. So if a common morph is attacked more frequently by a predator than a morph which is rare, how's that going to affect the fitness of that common morph? Will it be higher or lower than that of a rare morph? It will be lower, that's right. You don't want to attract the attention of a predator. That's going to reduce your fitness. Okay, so when a morph becomes common, it suffers higher predation, and that lowers its fitness. On the other hand, a morph which is rare suffers less predation, and its fitness decreases, and as a result, it's going to become more common over time. But guess what's going to happen eventually? That morph will become the most common one, and then the predator will return attention to that morph that was originally rare. The fitness that is high when the morph is low will become low in that situation reverses. So this is an example of negative frequency-dependent selection. Having a high, belonging to the morph which is most common is disadvantageous. And that puts a brake on any morphs becoming overly abundant and excluding the other morphs. Whenever a morph starts to become very common, the predator preferentially knocks it down. And that allows the morphs to coexist with each other. So this is negative frequency-dependent selection that allows the coexistence of these three color morphs. Now, in general, balancing selection is a name that refers to any kind of natural selection that maintains genetic variation in the population. That balancing selection will lead to a balanced polymorphism. You have the maintenance of two distinct morphs, or the genetic level of maintenance of alternative alleles for a gene that survive over the long term together, where neither morph or neither allele becomes overly dominant. Some examples of balancing selection include things like negative frequency-dependent selection, which we just talked about. Also, diversifying selection, that will maintain different morphs in the population. Heterozygote advantage, where the heterozygote is more fit than either of the homozygotes, that will also tend to maintain the coexistence of alternative alleles in the population. So those are all examples of balancing selection, selection that results in diversity being maintained within a population. Okay, now, remember this is our friend, the tropical mantis, with this amazing camouflage on this background of this orchid that it takes to live on. You can pretty easily understand how a trait like this camouflage could evolve under natural selection. It seems pretty obvious that camouflage is advantageous to an insect that has enemies like birds. This camouflage will help it survive, and that should improve it. So you can pretty easily understand how a trait like this would evolve under natural selection. But Darwin himself had trouble initially explaining certain traits that we see in nature. For example, this is a male peacock here. It's got this enormous train of tail feathers, which are very bright in colors along with the plumage on its own body. As a result, the peacock is very, very conspicuous to predators. And the tail feathers are an impediment to flight. The male peacock can fly, but it does so with great difficulty and very inefficiently. It's also very costly in terms of energy and nutrients to make these train of tail feathers like this. You can use those nutrients to make stronger flight muscles instead, for example. So why invest in producing this enormous train of tail feathers? It doesn't seem to provide any survival advantage. In general, Darwin noted that there seem to be a lot of animals that are brightly colored, in spite of the fact that they don't have any defenses. So we can't explain coloration as warning coloration, because a lot of animals don't seem to have any kind of defense that they're advertising. Here you can see a tiny pheasant, ducky, and a butterfly, all with very bright coloration. There's no chemical defenses in any of these animals. They're all quite edible to predators. And yet, this bright coloration seems to be making them very conspicuous. Why would natural selection allow something like that to evolve? It seems counterintuitive or counter to survival, and therefore counter to fitness. Well, Darwin noted that it tends to be males in particular that are often brightly ornamented. Here we see a pair of pheasants. This one is a female. You can see the fur coloration is much less conspicuous. It's sort of drab and cryptic or camouflage-like, whereas the male is one that's very brightly colored and very conspicuous. So he came up with an alternative theory to natural selection to try and explain why we see this type of color pattern, particularly in males. And that theory is we refer to as sexual selection, which is selection that occurs as a result of interactions between or within the sexes. And initially, Darwin thought of this as a kind of an alternative to natural selection, but now most biologists view it as just a special case of natural selection. We're still talking about traits that improve fitness, traits that improve reproductive success. There's two types of sexual selection. On the one hand, we have intersexual selection, which occurs when there's an interaction between different sexes. So when individuals choose mates that have specific traits that are not otherwise adaptive, that don't have any value for fitness other than the fact that they're helping be chosen as a mate. That's an example of intersexual selection. Now, in birds and mammals, females usually invest more in reproduction than males do. In mammals, females have to carry the offspring while they gestate. She has to provide them with nutrients while they grow. After they're born, she has to provide them with milk. The male doesn't do any of that. Females also can only produce a limited number of offspring in their lifetime because they can put this big investment into each one that they produce. There's long time spent nurturing the young, and that basically limits the number of times that females can reproduce. The same applies in birds. Although they don't provide milk to their young, females still have to make a very big egg, which is packed full of plenty of nutrients, which the males don't have to do. And that's a big metabolic drain on females. Males, on the other hand, produce sperm, which are very cheap, and metabolically they don't proliferate like awesome male. Males can produce sperm continuously throughout their lives. So males can fertilize as many females as they can get access to. And if you're a male, the best strategy to improve your fitness, therefore, is to just mate with as many females as you possibly can. Females, on the other hand, because they can only produce a limited number of offspring, they want to wait for the best possible male to combine their alleles with in order to increase the fitness of their offspring. So females tend to look for quality in mates, whereas males tend to be looking for quantity. So because females are choosier than males, they tend to have a stronger influence on male evolution than vice versa. Female choice results in certain traits appearing in males, but males don't exert as much choice as females, so they don't cause female traits to change. Now this leads to what we call sexual dimorphism, when males and females of the species look different. I showed you the example of the pheasants already. These are wild chickens. This is a male here, and the female, you can see once again, the female is perfectly colored, whereas the male is bright and showy. This is a very common pattern in birds. Females are often prickly, whereas the males are often bright in colors. Now, experiments have shown that females tend to prefer bright-colored males as mates. So brightly colored males tend to attract more females. And that's in spite of all the disadvantages that bright coloration would seem to have, that I just explained before. Bright-colored males are more vulnerable to predators. They waste a lot of effort making these big, bright feathers that don't provide any survival advantage. If a female chooses a male like that, then her male children will be saddled with the same handicaps. They're going to also have those bright feathers that don't seem to confer survival advantage. So why would a female prefer a male like this? Why would brightly colored males be preferred? Does anyone have any suggestions as to why that would be? Right. It could be an indication of overall health of the males. A brightly colored male is probably parasite-free. It probably doesn't have mites or other parasites that feed on the feathers of birds. Well, often these parasites will cause birds to have a sort of a dull or ratty appearance. A brightly colored male probably has a strong immune system. He's probably free of those parasites. Is there any other advantage to selecting a bright colored male? One, yes? The predators will be distracted. That's a good possibility. Maybe the predators will be distracted by the male. They'll go for him instead of the children. Yeah, that's a possibility, although that would mean that her children would also have that same problem. So why would there might be a trade-off there that could balance it.
It's kind of branching off the immune system. could brightly colored male indicate a more diverse gene pool, like more diverse gene?
In order to become, so that includes resistance to parasites? Oh, yes, yeah, exactly. A brightly colored male might have that genetic advantage, so yes, related to resistance to disease. He might have a combination of antigens that is particularly effective at avoiding parasites. Exactly. Often a brightly colored male will be a better forager than one which is less brightly colored. In order to make these bright feathers, birds need to be well fed, and sometimes the pigments in the feathers are actually derived directly from the feed. So a bright colored male is a good forager, and that's important for birds because males help provide food to the young. It's important to suggest that a bright colored male will be a better provider than one that is not so brightly colored. So there's a number of reasons why being brightly colored might have an overriding effect on fitness. Even though there is a risk of increased predation, there are these other benefits that might outweigh that might have a stronger effect overall on fitness. So that raises a more general question. Does female preference reflect male fitness? Are females really choosing males that are better, that are genetically more fit than the males which they're avoiding? One experiment to test this, to find out whether that's the case, was done with this critter here. This is a gray tree frog. And in this species, males sing to attract females. Now, some males produce relatively long, trill-like calls that last over a second. Others produce relatively short calls that only last about half a second per second. So there are basically two phenotypes when it comes to the calls that males produce. They can be long calls, or they can have short calls. This diagram at the top of this slide here is an example of a sonogram, which is a diagram that shows the frequency and amplitude of sounds made by animals. Here you can see the sonograms for a short calling frog, and here's a sonogram for a long calling frog. And basically, the sounds are identical in terms of frequency and amplitude. The only difference is the duration of the call. Short calling frogs use short ones, and long calling frogs. Females seem to prefer these long calling males. And once again, a long call would seem to make the male more vulnerable because he's advertising his position to predators as well as to females. That's going to make him more vulnerable to predators. So why would a female prefer that? Well, in this experiment, they took a bunch of female frogs and they divided their eggs into two batches. So they basically took all the eggs laid by one female and they fertilized half of those eggs with sperm from a short calling male, and the other half with sperm from a long calling male. And then they measured the fitness of the offspring that were produced. Those eggs eventually developed into tadpoles, which eventually developed into frogs. So they compared the fitness of the offspring of short calling frogs with the offspring of long calling frogs to see if there's any difference. Now, fitness is directly related to reproductive success. So ideally, the best way to measure fitness is to look at the total number of descendants that an individual leaves over several generations. But in an experiment, that's hard to do because obviously you're limited in terms of time and resources. So rather than measuring long-term fitness directly, biologists tend to measure what we call fitness correlates. Fitness measures, things that are likely to be reflective of fitness or likely to be related to fitness. So here there were three things that were measured. Larva growth, which usually related to fitness. A larva that grows, in other words, a tadpole that grows into a bigger frog would be more fit than one which grows into a smaller frog because a bigger frog can lay more eggs and produce more sperm. So basically size tends to be related to fitness. Larval survival obviously is related to fitness because a tadpole doesn't survive to adulthood, it's not going to reproduce. And time to metamorphosis is also related. That's the time it takes for a tadpole to develop into an adult frog. Basically, rapid development is advantageous compared to slower development because the sooner you become an adult, the sooner you can start reproducing, and therefore the higher the fitness. So in this case, it's short development time is advantageous and long development time. They repeated this experiment twice, in 1995 and 1996, and they measured these three. They took these three fitness measures of the tadpoles that were created, You can see that in 1995, there was no significant difference, like the NSC stands for, between short-polling and long-polling tadpoles. The growth of short-polling tadpoles and short-polling fathers was about the same as that of long-polling. However, survival was better for long-polling tadpoles, and time to metamorphosis was also better. You reached adulthood more quickly if they were fathered by a long-polling male. So overall, it seemed that in 2 out of 3 measures, the long-polling tadpoles showed better fitness than those that were fathered by short-polling fathers. In 1996, they did the same experiment again, and this time there was a difference in terms of larval growth. The long-polling tadpoles grew bigger. And there was also a difference in terms of metamorphosis time. Again, the tadpoles from long-polling fathers developed more quickly, although there was no difference in survival. But again, 2 out of 3 measures suggested that the offspring of long-polling fathers are more fit. So in general, there was a tendency for the tadpoles of long-polling males to have higher fitness than those of short-polling males. And that tells us that female preference, although it seems to be fairly esoteric, females seem to be selecting something that doesn't appear to be related to fitness. In fact, what they're selecting is a good reflection of the fitness of those males, and the fitness of the offspring of those females, in this case, chose the males that advertised higher fitness than the ones compared to the ones that they avoided. So that's an example of intersexual selection where, in this case, female choice having an influence on males. Now, the other kind of sexual selection is intrasexual, which results from interactions between individuals of the same sex. We often see this in mammals in particular. Often males compete for mates. These are bighorn sheep here. This one is the male on the left. On the right is the female. You can see that males are physically larger, and they tend to have these big horns, which they use to fight each other. Males will butt heads together, they will ram each other from the side, and so on. They tend to fight in order to secure mates for themselves. So the dominant male, which is usually the largest and best armed male with the biggest horns, tends to be the one that gets the most mates and has the highest reproductive success. So in this species, it's competition between males that results in selection for an increase in male size and an increase in the size of their horns. In this case, female choice doesn't seem to be a factor. It's not the females that are choosing larger males. Males are fighting it out amongst themselves, and the largest ones are the ones that are most successful. So in this case, it's only interactions within males that are causing this dimorphism to evolve. But at the same time, we still see dimorphism. We still see a difference between males and females as a result of this intrasexual interaction. Now, if we see a species that is dimorphic, how do we know whether that's a result of intersexual or intrasexual selection? Both types of selection can lead to sexual dimorphism, difference between males and females. This is a widow bird here, and this particular individual is male. You can see that it has ridiculously long tail feathers. Females don't have tails like this, they have relatively normal looking tails. So there's definitely dimorphism between the species, and males are different from females. It's also been noted that males compete with each other by defending territories. So there is some intrasexual competition between males that tend to fight for the best territories, and those males with the best territories will tend to have better mating success. So, which type of sexual selection can account for the dimorphism that we see in the species? There seems to be a possibility that it could be intrasexual, but we can't rule out intersexual either. So which kind of selection resulted in this development of these very long male tail feathers? Well, here's an experiment we've done to try and figure out which type of selection is more important. In this experiment, they took male birds and they subjected them to various different treatments. Some of them were clipped so that their tails were artificially shortened with scissors, basically, cutting them short. In other cases, they took feather extensions and they glued them onto the tails of the males to create even more ridiculously long tails. And then they also had control birds which had unmanipulated normal sized tails. And then they measured the reproductive success of these three types of males. They looked at the number of mates per male. And you can see that those with shortened tails had lower mating success than those with normal tails, while while those with lengthened tails had vastly increased mating success compared with those that had normal tails. Those with the crazy long tails had much greater success attracting females than those which were normal. They also observed that tail length did not seem to have any effect on ability to defend a territory. So whether they had short, normal, or long tails, males seem to be equally capable of defending their territories. So this experiment seems to suggest that intersexual selection alone seems to account for the tail length of males in the species. Basically, female preference selecting males with long tails, which is causing the region to straight, and competition between males is not a factor. Now that basically finishes the material that we're going to cover for test one. I've got a few practice problems on that material. We can work on together, so we'll do a couple before we take our break. We'll do a couple more afterwards. So you can get out and put this. In humans, a widow's peak is a dominant trait, while a straight hairline is recessive. Widow's peak, remember, is kind of a Dracula type pointed hairline. Straight hairline, straight hairline. The widow's peak tends to be dominant over the straight. 51% of the people in the population have a widow's peak. What is the frequency of the allele for a straight hairline? Assume the population is only 1 to 1 million. And the polling looking to send your answers whenever you're ready.
First of all, remember your two equations. Problems like this. Each remember these two equations. P plus Q equals 1. P squared plus 2 equals Q squared equals 1. The idea is to try to figure out what information you're given in the which of these five information corresponds with, what information is being asked upon. It says here, 51% of the people in the population have a widow's peak. Which of these five terms does that correspond to? You're in P squared plus 2PP, that is right. The widow's peak is a dominant trait. So there's more than one genotype that can produce that trait. It could be homozygous dominance, or heterozygous. Both of those will produce a widow's peak. So in this case, there's two terms here that information goes. Now, basically, what are being told in this question? Frequency of widow's peak is 0.51. And that corresponds with P squared plus 2. When we solve for P or Q with that information, we've got two unknowns here. We've got both P and Q. So we can't just plug that 0.51 in to the equation and get an answer. But is there another way to do this? This number of 0.51, what kind of frequency is that? Is that a trait, a genotype, or an allele frequency? It's a trait. If we know the frequency of widow's peak, what's the frequency of a straight hairline? 0.49. Frequency of a straight hairline. That would be 1 minus 0.51. And which of our five terms is that first one? Q squared. Q squared. And we can't calculate P with this. We can easily calculate Q with Q squared. Just take a square root. Therefore, Q, the frequency of the potential wheel, is 0.7. Square root of 0.1. And the question back is actually asking you, what is the frequency of the recessive allele? It's basically asking you for Q. It's asking what is the frequency of the allele for straight hairline. It's asking you for Q. Recessive allele. You see the answer, the correct answer is E. Many of you get 0.49, which is the frequency of the homozygous recessive genotype, frequency of the straight hairline. So about 3/4 of the way towards the answer, but you still have one more step to do, which is to take the square root of this in order to actually get the frequency of the allele for a straight hairline. This is going to correspond to Q squared, not Q. Take the square root, and it is 7. Remember, figure out what information you're told, what kind of frequency is it, is it a trait, is it a genotype, or is it an allele, and what is it you're being asked to find. And remember these five terms here. Always relate that information back to these five terms. Once you've done that, almost always plug in numbers and solve it. Most likely, it's meaningful. In some cases, if you're told the frequency of the dominant allele, and you're not told the frequency of the recessive allele, in most most cases, you go before. Let's try another one. In heat measurements. Here's another example. It is on rocks that have lichens growing on them. You see there's some surrounding lichens, and this is the actual insect that's added in there. The borax and the heads. Again, you see this amazing camouflage that is involved here. Which to match the color of the rock. That's that insect. Now these mansions, individuals of an intermediate shade of green, which closely matches the vegetation of the rest are less likely to be eaten by birds than those with a lighter or darker shade. What type of selection has produced camouflage coloration of these insects? Red ink, colorization, disruption, colors are frequency dependent, or radiation dependent. In their intermediate.
There's no dialogue.
Okay, 5 seconds. Great. 2/3 of the big B stabilizing section. That's correct. And we can rule out frequency dependence here because there's no indication that being a particular shade of green is more advantageous depending on whether it's common or rare. Whenever you see that kind of phrase, and you see that fitness depends on frequency, that it varies depending on whether something is abundant or rare, then you should think frequency dependence. In this case, there's no indication of that, so you can rule out GP right away. And it says individuals of the intermediate shade of green are less likely to be eaten by birds. So individuals that are very dark green or very light green, in other words, the tails of the distribution, those are the ones that are going to be preferentially eliminated. Natural selection is acting against the extreme individuals, leaving the intermediate phenotype, and that one becomes most abundant. So that's a stabilizing selection. Okay, I think this should be a good place now. So we've got a few more problems that we can do when we come back. Look to give our answers. The negative frequency dependent selection. Frequency of a morph is always negatively correlated with what? In other words, what goes with the axis here? Is it rate which is attacked by a predator, fitness, or its survival rate? Already got lots of answers. I'm going to close that. Oh, okay, sorry. Take a minute to answer. Okay, hold on a second. All right. Most of you, more than 80% is being fitness, right? In negative frequency dependent selection, the frequency of the trait is always negatively correlated with the fitness associated with that trait. It may also be correlated with survival rate, but only because survival rate is ultimately increased fitness. The most important thing is that reproductive success is lower if the trait is more abundant. So it's fitness that ultimately determines that is negative fitness. Okay. Let's find out. The moth population shown below is not in hardy worm equilibrium due to strong selection against the recessive phenotype, against white moths. Here we see the population got 250 individuals who are 50-50, 500 who are 50 small meat, and 0 who are small whole white moth and malignant. Now, if natural selection were to suddenly stop, in other words, all the birds in that environment suddenly died out, so there was no more predation, how long would it take the population to return to hardy wandering equilibrium? Assume there's no overlap between generations, so after things are laid, all moths die in the next generation. Would it take 1 generation, 2 generations, 3, 4, more than 4, or do not answer this question? Polling is now open to consideration of it. 1/3 of you picked F, and the rest chose a variety of other answers, so quite a lot of spread here. All right. Let's take this up. Now, first of all, the answer, I'll tell you right now, is one generation. A is the correct answer. No matter how far away from equilibrium a population has strayed, if conditions for Hardy-Weinberg return so that population stops evolving, immediately, the next generation, it will go back to Hardy-Weinberg equilibrium. Let's think about why. If gametes combine together at random, in other words, there's no natural selection, it doesn't matter what genotype you have, you're equally likely to reproduce. If mating is random, there's no preference of one genotype over another, and so on. In other words, if all 5 of the conditions for Hardy-Weinberg are met, then the odds that any one sperm or egg will have a small allele will be equal to the frequency of that allele Q. And the odds of 2 of those alleles coming together to conceive an individual will always be equal to Q squared. It doesn't matter whether the allele is present in homozygotes or heterozygotes. The odds of choosing 2 of those alleles being completely at random will always be equal to Q squared. It doesn't matter whether all the alleles are homozygotes, whether they're all heterozygotes, or there's a mixture of the 2. The odds of picking 2 in a row will always be equal to the frequency squared. Okay. The odds of any one sperm or egg having a big P allele are therefore P, and the odds of having a big B genotype will be P squared. That's the odds of 2 of those coming together. The odds of inheriting a big B from father, small b from mother, times Q, small b from father, and big B from mother, times P. So the odds that either of those things happening as conceiving a heterozygote, therefore, would be 2P. So if we go back to this population here, if we have 250 big B's and 550 small b's, if I pick 2 alleles at random, the odds of picking 2 small b's will be equal to the frequency of small b squared. If we're choosing totally at random. So the answer is always one generation. When evolution stops, immediately Hardy-Weinberg returns to equilibrium. It doesn't matter how far away from equilibrium the frequencies have strayed as a result of natural selection or whatever it is that's causing evolution. Okay, now, let's try it. If natural selection stops, what will be the genotype frequency of the next generation of moths? Here's the current generation. What will be the frequency of big B, big B, big B, small b, small b, small b, if natural selection were to suddenly stop? You could send your answer in another way. that. Looks like A, B, and C are all popular choices. All right, we've got 250 big biggies, 500 big small bees. Question? Okay. How many moths do we have altogether? How many alleles do we have altogether? 1,500. Maybe 2 times the number of moths. Okay, how many big bee alleles do we have? 7, let's see, we've got 250 times 2 here. Remember, big B that we're calculating. We've got 250 moths with 2. We've got another 500 with 1. So that's 500 plus 500, that's 1,000. So what's the frequency of the dominant allele here? What do we divide this number by? P is going to be 1,000 divided by 1,500, 0.67. That's the frequency of the dominant allele. Number of small bees. We don't have any small bees. We have 500 individuals with 1. It's just going to be 500. If we divide 500 by the total number of alleles, we get 0.33. So P and Q add up to 1.67. Okay, so now we figured out what our allele frequencies are. Hardy-Weinberg conditions are being satisfied, and we can use those to determine what the genotype is. Frequency of big B should be 167 squared. Squared, and that's 3 about 24.4. Put that in the calculator. Frequency of big B small b is going to be 2 times 167 times 0.3. Also works out to 0.44. The frequency of small b small b is equal to q squared, which is 0.3 squared, which is 0.11. That's actually 44.4 versus 11.1. So B is the correct answer. Okay, so to figure out what the Hardy-Weinberg predictions are going to be for the next generation, you need to figure out the allele frequencies, and then use those as calculators. That's basically how Hardy-Weinberg works. It predicts the genotype frequencies using the allele frequencies. The first step here is to figure out what are the actual allele frequencies, and then plug those into Q squared, Q squared to get the genotype. All right. Let's go ahead. In an isolated population of fruit flies, 4% of the individuals have pink eyes, homozygous recessive condition, and 96% have the dominant black eye. What percentage of the population are black-eyed carriers of the pink eye allele? See the population in Hardy-Weinberg predictions. What we're looking to see the answer number. get the answers from you. Give me 15 more seconds. I'll close that. And A is the most popular answer, and that's also correct. 32% is right. Only about 40% you picked up, is quite a spread of other answers. Okay. Remember our two equations here? You have to figure out what information we're being told, and which of those 5 terms it corresponds to. In an isolated population of fruit flies, 4% of the individuals have pink eyes, a homozygous recessive condition, and 96% have black eyes. This number 4% here. That's the frequency of pink eyes. Which of our 5 traits, which of our 5 human terms does that correspond to? Frequency of pink eyes 4%, sorry. Q squared is right. Although this is the frequency of a trait, if it's a recessive trait, there's only one genotype that can give us that homozygous recessive. So 4% is Q squared, the frequency of a homozygous recessive genotype. And what will be asked to find? What percentage of the population are black-eyed carriers? Which of the 5 terms are we looking for? Heterozygous. When you see the word carrier, you should think heterozygous. Being asked to find the frequency of heterozygous. Those who have black eyes will be carried pink eyes. So which of the 5 terms is that? Q, right? All right, so we're given 2 squared. We're given Q squared. We're trying to find 2P. Okay, well, first of all, we take the square root of this in order to get Q. 4% is 0.04. The square root of 4%. The square root of 0.04 is 0.2. That's going to give us Q. Take the square root. First of all, if you're given numbers in percentages, convert them back to a proportion before you do your calculations. It's much easier to do using proportions rather than percentages. So you convert that principle to a proportion of 0.04, take the square root, that gives us a Q of 0.2. So what's P going to be? 0.8, right? 1 minus 0.8. Now all we do is plug in. 2 times 0.2 times 0.8. 2 times 0.16, which is 32%. So that's how we arrive at the answer. Okay, so once again, just be careful about reading the question, what information you're given, and what information you're being asked to find. Remember those 5 terms and those 2 equations. Okay, now test number 1 covers everything up to this point, including the type of problems we just did. Everything that I'm going to talk about for the rest of the class today will be covered on test 2. So you're not going to be responsible for the material on the test. Still have 15 more minutes left. And we're not going to get to speciation today. I will talk a little bit about some of the other causes of evolution besides natural selection. Okay, we saw that there's 5 things, and we've only been talking about one of them so far, natural selection. The second one on the list is genetic drift. This can also cause evolution to take place. Genetic drift. Simply a change in genetic structure in vitro organisms. In other words, a change in the allele or the genotype because of a random accident that might kill some individuals in experiments, regardless of how fit those individuals are. And the science that the fact that there's no natural selection. Another assumption made by Ben Weinberg is that populations are infinitely large. Big, infinitely large populations, random accidents are not likely to affect the frequency of the alleles. In a finite population, the random death of certain individuals will affect the frequency of alleles of individuals that are left behind. Let's illustrate that. Again, with a document hammer example. The genetic drift. So let's say that once again, I'm dealing with a population of moths, which includes 5 individuals who are big B, 10 who are big B, small b, 5 who are small b, small b. These first 15 moths here will have a black appearance. The last 5 have a white phenotype. Okay, what's P and Q for this population? We've got 20 moths altogether, so we have 40 alleles. We've got 10 plus 10 is 20 big 20 out of 40 gives us P of 25. So we also know that Q would have to be 0.5, but we can also calculate that a long way. There's 10 small b's there, and 5 times 2 is another 10, that's 20 out of 40. So Q is also 0.5. Okay. So we have here a relatively small population, just 20 moths. Now let's say that a frost comes along and kills 80% of these moths at random. Okay, unlike birds, which preferentially select one color over the other, frost doesn't discriminate between white and dark moths. It just kills moths randomly. And now, there's 20 moths, that means there's going to be 4 left. We eliminate 80%. Let's just say, for the sake of this example, that we're left with no big B babies, 0, 3 big B small b's, and 1 small b small b. That's quite a feasible outcome of this kind of event. Okay, what are P and P now? Okay, well, I only got 4 moths left, so I've got 8 alleles. P is going to be, so there's 3 big B's and 2 big B's here, so we've got 3 out of 8, which is 0.375. And the recessive allele Q, we've got 1 there with 2 copies, plus 3 that have 1, so that's a total of 5 copies out of 8. It gives a frequency of 0.625. All right, so we started with P and Q of 0.5. We finished with P and Q of 0.375 and 0.625. The frequencies have changed. That's basically evolution. This population just evolved as a result of a completely random accident. Survival of some individuals over others, purely by chance. That has changed the allele frequencies, and it's also changed the phenotype frequencies. Big B small b is now 75%, whereas before it was 50%. Small b is still 25%. You can see that basically, just by randomly eliminating certain individuals, if the population is small to begin with, that's likely to alter the allele in the
into the freezer.
That's genetic.
I want to.
That can also cause populations to undergo genetic change and therefore evolve. Now, genetic drift tends to decrease the genetic diversity of a population because alleles that are rare to start off with are likely to be eliminated by random accidents. There's only a few individuals in a population that have to be carried a rare allele. And if those individuals get hit by lightning or if a tree falls on them or something like that, that allele will be completely lost from the population. So random accidents can eliminate rare alleles entirely. But that's going to be less likely in a large population than in a small one. In a big population,
Even if the allele is rare, so this will be 100 individuals that have that allele. It's unlikely that random events are going to completely eliminate all those individuals. find out history is that genetic drift tends to decrease genetic diversity. Variables less likely to be eliminated in a big population than they are in a small population. Now, a special case of genetic drift is the bottleneck effect, which is genetic drift that occurs after massive mortality. Most individuals are populated in that way. Change the battery.
Better. This animal here, it's a northern elephant seal. And in the 1890s, this species were on the brink of extinction. The seals had been heavily hunted for many decades as food. And by the end of the 19th century, the world population was down to just 20 individuals. Only 20 of these seals left in the entire world. Then laws were passed in order to protect them. Those 20 individuals began to reproduce. And now their population has increased back to a seemingly healthy 100,000 individuals. Seems like it should be a lot more safe. However, researchers are still concerned about the long-term survival of the species. When they examined the genetic structure of the population of elephant seals today, they found that in many cases, for many genes, there was basically no genetic diversity. There was a single allele that was fixed for a large majority of the genes that they looked at. When they looked at 24 different genes, they found a single allele was fixed in all 24, meaning that the frequency of that allele was 1 or 100%. So basically, every individual was homozygous for the same allele. Now that's not a good thing in terms of the future potential of this population to adapt to change, because if a new disease comes along, or if there's some other change in the environment, there might not be any individuals that have genetic variation that will give them resistance to that change. It will enable them to survive and regenerate the population with a lot of seals dying. Now, they also compared those same genes in another species, the southern elephant seal, which was less than 300. And when they looked at those 24 genes, they found that only 7 of those 24 had fixed alleles. So it appears that the near-death experience of the species, where basically the whole population was reduced to just 20 individuals, and then it was regenerated just from those 20 individuals, that had the effect of eliminating a lot of the genetic variation that used to be present in the species. So that's an example of what we call a bottleneck effect. When genetic diversity decreases as a result of the random elimination of a large majority of individuals, leaving only a few to regenerate those numbers. And as a result, only the alleles that survive in those few individuals will be the ones that are present after the numbers have reduced. Another case of genetic drift is known as the founder effect. This happens when a few individuals colonize a new environment and start a new population from an initially small number of individuals. Again, that's going to result in a limited gene pool in a new population. Let's say we have a population of white and black moths, and a few of these individuals leave and start a new population on their own. That new population, because it's based on just 2 individuals, will have much less genetic diversity than the original parent population. It's basically been grown from a small sample of genetic diversity, which is very useful. So we tend to see less genetic variation as a result of these founder effects. So the population is basically generated from a small number of colonizers. It's been suggested that the founder effect might also be an alternative explanation for the high frequency of the Tay-Sachs allele in Hashimoto's disease. Remember we talked before about the high frequency of the Tay-Sachs allele in those populations possibly being due to the presence of tuberculosis during the Second World War. Another alternative explanation might be that it's just a case of genetic drift, that individuals who survive just happen to have a high frequency of size. So there really is no selective advantage there. So that's still a matter of ongoing debate as to whether the genetic advantage there. Another assumption of Harding Weinberg is that populations are close, so there's no integration or integration into or out of the population. But in fact, most populations are not closed. Individuals do move in and out, and this is referred to as gene flow in population movement. So it's the exchange of alleles between different populations. And that can occur either because of physical movements of individuals leaving one population into another, or it can occur because of gamete feeding. In the case of plants, for instance, individuals are not able to get up and move around, but their pollen can be dispersed over very long distances. It's possible for alleles from a forest several kilometers away to get into a local forest and introduce new alleles out. So in gene flow, let's say we have a population initially that's mostly black, another one that's mostly white, and then a few individuals leave population 1 and move into population 2. That's migration or gene flow, which alters the allele frequencies in both. The frequency of the white allele has gone down in this parent population, and the frequency of the black allele has gone up in the population that you can see humans. So migration also between populations that are not close, that changes the allele frequencies, the genotype frequencies. And unlike natural selection, gene flow often produces changes that are not adaptive or counter-adaptive, because new alleles are likely not to be adapted to local conditions. If they're coming from a population outside the area experiencing different conditions, they're probably not going to be adapted locally. If we look at mammals on volcanic islands, for example, where there is no gene flow with the mainlands, so in other words, we have islands that are very distant from the mainland, very far out of the ocean, the mammals on those islands tend to have dark fur, which closely matches the color of the rocks that they live on. So they have camouflage. Those rocks are even, they can be dark in color and dark for the animals. But when you have islands that are close to the mainland, often you get exchange of individuals back and forth. So individuals can swim from the mainland out to the island and vice versa. As a result of that, there's an exchange of alleles between the mainland population and the islands. And as a result, the fur on the islands tends to be less dark, tends to be less well matched to the surrounding coloration. So that results in a change which is counter-adaptive rather than one which is adaptive. Gene flow often produces genetic change which is actually bad for survival or produces that, it produces change that is reducing fitness counter-adaptive. We're going to leave the last two parts of evolution for our next class. We'll end it there. Remember, I lost